Welcome back to Future Mind Jane AI Data Science Podcast. I'm your host Manav. I'm thrilled to have you with me for our 11th episode. Last time we dove into the fascinating world of reinforcement learning, exploring its core concepts, methodologies, real world applications. Today, we are going to shift our focus to another captivating topic within the realm of AI, generative adversarial network, that is GANs. These networks have revolutionized the field of generative modeling and are responsible for some of the most impressive advancement in AI over past decades. Let's start. Generative adversarial networks, that is GANs, are a class of machine learning framework designed by Ian Goodfellow and his colleagues in 2014. GANs consist of two neural networks, the generator and the discriminator, which compete against each other in a zero sum game. The generator creates data while the discriminator evaluates it, and this adversarial process pushes both networks to improve, resulting in generation of highly realistic data. Components of GANs: generator and the discriminator. Generator: the generator network takes random noise as the input and produces data that resembles the training data, and its goal is to generate data that is indistinguishable from real data. And second, discriminator: the discriminator network receives both real data and fake data generated by generator, and its task to distinguish between the real and fake data accurately. It outputs probability indicating whether the data is real or generated. Training process of these GANs involves back and forth process of where both networks improve simultaneously. Step 1: the generator creates batch of fake data from random noise. Step 2: the discriminator evaluates this fake data alongside real data from training set. Step 3: discriminator is trained to distinguish between real and fake data. And step 4: the generator is trained to produce better fake data to fool the discriminator. This iterative process continues until the generator produces data that discriminator cannot easily distinguish from real data. Discriminator loss: types of GANs. There are several variants of GANs, each designed for different tasks and improvement over basic GANs architecture. DC GANs, Deep Convolution GAN, utilize convolution neural network CNN to improve image generation quality. C GANs, conditional GANs, adds additional information labels to both generator and discriminator, allowing for the generation of specific classes of data. Cycle GANs, used to image translation without in paired examples, such as transforming photo into paintings and vice versa. Style GAN, developed by NVIDIA, this GAN's architecture is known for generating high resolution photorealistic image with control over the style of generated images. Application of GANs: image generation. GANs can generate realistic image from scratch, including human space, face, landscapes, and objects. These images are often indistinguishable from real photographs. Real image to image generation. Image to image translation. GANs can transform image from one domain to another. Example include translating sketches to photo, black and white to image to color, and day scenes to night scenes. Data augmentation. GANs can generate additional training data for machine learning models, especially when the real data is scarce. These improve performance of model by providing more diverse training samples. Art and creativity. Artists and designers use GANs to create unique artwork, generate new fashion design, produce innovative visual content. Video synthesis. GANs are used to generate realistic videos, create deepfakes, and improve video quality through techniques like super resolution. Music generation. GANs can generate music composition by learning from dataset of musical pieces, producing original music that follows the learned style and patterns. Challenge in training GANs. Despite their potential, GANs are notoriously difficult to train. Some common challenges include mode collapse. The generator produces limited variety of output, failing to capture the full diversity of the training data. Non-convergence. The generator and discriminator do not reach stable equilibrium, leading to oscillation and failure to produce realistic data. Vanishing gradients. Discriminator become too confident, causing the gradient to vanish and hindering the generator's ability to learn. Technique to improve GAN's training. Feature matching. Instead of directly comparing generated and real data, the generator aims to match features extracted from intermediate layer of the discriminator. Mini batch discrimination. Introduce the form of batch level comparison, encouraging the generator to produce diverse outputs. Spectral normalization. Stabilize the training by normalizing the spectral norm of the discriminator weights, ensuring better gradients. Two time scale update rule. Adjust the learning rates of the generator and discriminator independently to stabilize training. Ethical consideration and defects. One of the most controversial application of GANs is the creation of deepfakes where realistic image or video of people are generated and altered to show them doing so saying things they never did. This raises the significant ethical legal concerns regarding privacy consent and misinformation. Regulation and countermeasures. To address these issues, researchers, policymakers are developing regulation and countermeasures including detection algorithm tool to detect whether the image or video is deepfake, helping to identify manipulated content. Watermarking metadata. Embedding hidden makers or metadata to authenticate real content and distinguish it from generated content. Legal frameworks. Establishing legal standards and consequences for the creation and distribution of deepfakes without consent. Future direction. GANs continue to evolve. Several promising research directions are being pursued. Improved training stability. Developing new techniques to ensure stable, efficient GANs training and reducing issues like mode collapse and non convergence. Enhanced control. Providing more control over the generation process, allowing for the creation of highly specific and customizable outputs. Cross mode modal generation, expanding GANs to handle multiple modalities such as generating text from images or vice versa, enabling more versatile AI application, integrating with other AI techniques, combining GANs with reinforcement learning, NLP, other AI methodologies to create more robust and capable of AI system. Thank you for joining me today on this Future Mind Genie AI Data Science podcast. I hope you found this exploration of generative adversarial networks as fascinating and enlightening as I did. Make sure you subscribe so you don't miss any upcoming episodes. Until next time, I am Manu signing off. Stay curious, stay inspired, keep exploring. Thank you.